Well, hello everyone. In this video, I wanted to present a conference work that I made for the International Symposium on Electromobility at Guadalajara, Mexico. The title of this work was Hammerstein Models for Rotor and Winding Temperature Estimation of a Permanent Magnet Synchronous Motor. The authors of this work were Eric Axel Martinez Rijos, Irvin Aguilar Zamorate, Saulius, Renato Galucci, and Nicola Matti. Okay, the outline of this presentation is as follows. First, I will make a brief introduction about the topic, then I will talk about the materials and methods, the results, the discussions, and the conclusions and future work. Permanent magnet synchronous motors are widely used in many applications due to their high power and torque density. And they are widely used in electric powertrains, wind power generation, and robotics. However, these motors are susceptible to faults. These faults could be electrical, mechanical, and magnetic. And these faults are caused by stress during prolonged operation and varying power source and load parameters. And if we talk about, in particular, about the magnetic and electric faults, they are produced by the heat generation inside the machine, okay, that also increases the temperature, which can lead to the following faults: the magnetization of the permanent magnets using the motor, or the melting of the isolation in the windings. And the magnetization also reduces the machine's torque capability, and metal isolation can produce short circuits. So based on these two factors is why we are interested in considering these two, the temperature, no? Because if we increase too much the temperature, basically we are reducing the magnetic flux of the machine, which also is correlated with the torque capability, no, of the motor. And also, if we melt the insulation of the windings in the motor, we can produce short circuits. Okay, the temperature monitoring is essential for controlling the machine effectively and prevent thermal overloading. And since the temperature is a crucial factor in order to prevent electrical or magnetic faults, in the literature we can find different approaches in which we can estimate or measure the temperature of the machine. We can use, for example, sensors, but they require structural modifications and also they can be costly. Also, you can use finite element analysis or computational fluid analysis, but the problem of these two methods is that they are time consuming and they are not feasible to implement in real time. And also we can use thermal and electric models. But the problem of thermal and electric models is that estimating their parameters can be challenging. And another approach is to use data-driven methods. And we can classify the data-driven methods used for permanent magnet synchronous motor estimation between two methods. We have static and dynamic. Static methods basically refer to use machine learning techniques such as the support vector regression, the k-nearest neighbor, and regression trees. And dynamic methods are deep learning techniques that can that work like in an autoregressive form, like the recurrent neural networks and the temporal convolutional neural networks. There is a problem with data-driven methods. First is a lack of interpretability, since they behave as black box methods. Also, machine learning requires large sample sizes and training times. And on the other hand, in gathering sufficient quality data could be time-consuming and unrealistic. Okay, as we can see, the literature has already tackled with a vast plethora of methods the problem of temperature estimation in permanent magnet synchronous machines. The problem here is that, and in particular case of data-driven methods, is that we have a lack of interpretability. We need many data to estimate these techniques, and also gathering sufficient quality data could be time-consuming and unrealistic. So the proposal of this work is to use a method that is called the Hammerstein-Wiener models. Hammerstein winner models are composed of three elements. We have an input nonlinearity, a linear time invariant block, and an output nonlinearity. And here, one key aspect to consider is that for the Hammerstein model, you only need the input nonlinearity and the linear time invariant block. But the advantage of using this approach is that we can combine some of the physics of the system with a data-driven method. So we can generate, for example, a linear model that is in order to um, fill this linear time invariant block of the Hammerstein model, and maybe we can use a nonlinear function like a simple neural network as the input nonlinearity. So in this purpose, or in this line, we have proposed to use as the linear time invariant block of the Hammerstein model a fourth-order Loom-parameter thermal network of the permanent magnet synchronous motor. As an input nonlinearity, we are using sigmoid neural networks. In particular, we are using one neuron sigmoid network. Okay, so for the data set that we use to estimate this Hammerstein model, we use a 200 kilowatts radial flux permanent magnet synchronous motor with surface mounted permanent magnets in the outer rotor and distributed winding for traction applications. And well, we apply three driving cycles. We apply a driving cycle to the motor in order to have a thermal response of the machine for different inlet coolant temperatures of 20, 40, and 60 degrees. In this regard, in figure 2, you can observe that we are showing you the driving cycle that was used to produce the thermal response in the machine. In this regard, we were using a preheating period for certain amount of time. Then we apply the Federal Test Procedure 75, and then we apply another preheating period, and then we apply the WLTC number 3 driving cycle. These two driving cycles were selected because they are high demand driving cycles, typically used for testing vehicles. And well, you can see at the top the normalized torque, and at the bottom the normalized speeds of the motor. Well, another important factor is that, well, this is a diagram or a cross-section of the machine. Here in the number 1 and 2, we are showing you the positions of the temperature sensors used to estimate the temperature in the windings. And in the label number 3, we are showing you the place of the temperature sensor in order to estimate the temperature of the magnet. And well, to validate this process or the fitting of the Hammerstein model, we use a threefold cross-validation process in which we use some part of the data for training the model and the other one for validating. And well, we basically switch the driving cycles that we had for the different coolant inlet temperatures, and we take the performance of the validation fold and then average the results. And to measure the performance, we base the analysis on three metrics: the mean square error, the root mean square error, and the mean absolute error. Okay, so as I mentioned before, in order to fit the Hammerstein model, we use a four-order Loom-parameter thermal network. In this regard, we are using a four-order Loom-parameter network of fixed parameters. This is important to note because, well, in the original work in which this thermal circuit was proposed, that is the work of Walsheet, that is reference 9 of this work. Well, the thermal resistance between the coolant and the stator yoke depends on the coolant temperature, and well, the temperature surrounding the permanent magnet also depend on the speed of the motor. Okay, so for this study, or for this first approximation, we only consider we assume that all these parameters, the resistance, were fixed. And well, in order to estimate these parameters, we use the particle and smart optimization. Also, the cost function was the square error, and the identifying model was discretized via zero-order Hall and considering a sampling time of 2 seconds. And in table 1, you can see the results of the identified parameters. Now, for the Hammerstein model, what we did was to Well, for the linear block, we use the fixed parameter for ordered LPTN. And well, just to remember that the inputs of this model are the stator yoke power loss, the stator winding power loss, the stator tube power loss, the permanent magnet power loss, and also the ambient and coolant temperature. And while following the approach of the Hammerstein model, we apply the input nonlinearity that in this case was a one neuron sigmoid network applied to the inputs of the power losses, as we can see in this image. Also, to estimate this model, we fitted the model using the 11-Markov algorithm with 100 iterations and the pulse of the LPTN, or in other words, the eigenvalues of the LPTN were fixed during this estimation process. And the above led to the results presented in table 2, in which we are showing you the results of the LPTN in terms of the mean square error, the root mean square error, and the mean absolute error, along with the corresponding standard deviation. And in table 3, we are showing you the cross-validation results of the Hammerstein model. If we compare table 2 and table 3, we can see that in general, there is a reduction in the error when working with the Hammerstein model. And well, here in figure 5, I'm showing you the comparison of the thermal response of the models compared with the thermal response of the measured temperature for both the winding and the top. In the middle is for the magnet, and at the bottom is the error across time. And in the right, we are showing you the performance of the Hammerstein model. If we compare the two graphs, we can see that the Hammerstein model has a lower error for both the winding and the magnet across all the driving cycle periods. So, well, in conclusion, we can say that this work proposed using the Hammerstein models to estimate the winding and magnet temperatures of a permanent magnet synchronous motor. The results, well, the fixed parameter LPTN attained an average mean square error of 31.66 square Celsius degrees for the winding and 6.00 square Celsius degrees for the magnet. The Hammerstein model attained an average mean square error of 1.98 square Celsius degrees for the winding and of 2.043 square Celsius degrees for the magnet. Future work, well, we are considering to incorporate the varying LPTM parameters to estimate the Hammerstein model because, well, in this case, we assume that these parameters were fixed. And also we are working in the real-time implementation of this model. So, well, we want to acknowledge the European Commissions and also LAFA Propulsion Technologies for providing financial aid and also the data set used to perform this research. These are the reference of this study, and thanks for your time and attention.